So yeah, if you see Mr. Haiduku, you might thank him for the apples. He told me to tell you that Newton brought them for you. So, all right, let's see here. All right, so here's what I want to do today. So most of today is going to be some time for you to work on the syllabus, but I do want to talk about momentum in 2 dimensions today. We'll take some questions over the homework. I want to point out to you what's coming up. So I'm pretty good. Most of the due dates on your syllabus, if you're following the due dates on the syllabus, they should be right with one exception. I'm postponing the due date for the elastic collision, which is 7/4/5. So it says that it's due Thursday, but I'm going to change that to Tuesday. So there's that. So at this point, you should have turned in your project sources. Hopefully you turned those in Friday. If not, tomorrow's e-learning day is a good time to make sure that's done. You should have finished the first 2 sections of the syllabus. So that's what should be done at this point. After today, you can do the elastic collision problems, which we learned last time. You can do the 2-dimensional problems, which is 7.7. That's going to be new next Thursday. Also, the next time I see you will be Friday, right? Yeah. Next time I see you will be Friday, and that's when we're doing the egg drop lab. So remember, you need to build an egg drop device before Friday, and that's going to be what my e-learning assignment is for you tomorrow. Remember, for the egg drop lab, under 200 grams, all I mean by that is, I have 200 grams, you're not sure about it, but basically it just means like, you can't put it in a container of peanut butter or something like that. But you need to bring a device that that we can put an egg in when you get here, and then we can drop it off the commons balcony, and it can hopefully survive. So that's the plan for what we're doing Friday. Yeah, great. Say one more time. I've heard it being used. I've never done. Usually, when I've done it, I've actually done it with just sheets of paper. So I've never actually seen it done. But I know that like it's something that works. Like I know that if you don't put like I don't know, has anyone that done an egg drop lab in another class at some point, like do they want to do the peanut butter thing, or no one want to do the peanut butter thing? I just heard it's a thing that works because it kind of really protects the egg and keeps it from jostling around. But I want to be more creative than that. So, yeah. An airship? All right. Looking forward to seeing it. Yeah.
You said it's like 200 grams with or without the egg?
With the egg. The egg itself is about 50 grams. So, yeah. And like I said, if you feel this right, you pretty much like if you're doing things with like plastic bottles, with paper, with cotton balls, plastic baggies, like you're not going to get close to this, right? If you're like, I can't even think about a reasonable thing other than peanut butter. I can't think of a reasonable thing that would be heavy. I don't know, like if you put connected some wall, like put a water balloon around it. I don't know what it would be. Like I said, I can't think of any reasonable way that you would get heavier than this anyway. But any other questions about that thing, the drop device? So that's all I'm going to have you be working on the e-learning day. Also, just for and all of these, again, all these, I tried really hard because there's a lot of due dates in this. Your syllabus really walks you through them. I'm planning on Wednesday of next week to do a homework quiz on elastic collisions, which is the 745. So that's why I want that due on Tuesday. All right, cool. What questions over the homework can I answer right now? 18? So if I recall, we talked about 18, maybe conceptually last time. But we can kind of go into a little bit more depth here. So the idea is I have a ball that sort of bounces off here. And remember last time we talked about which way will the impulse have to point in order, which way will the impulse have to act on this ball in order to make it do that? Remember the direction? Yeah, so Malachi's pointing this way, right? This is the direction the impulse has to be, right? Because remember, impulse is equal to the change in momentum. And what you can do is you can calculate what the initial momentum is and what the P prime, the final momentum is. But each of these has an X component and a Y component, right? That has a PX and a PY. This would have a PX prime and a PY prime. And what you should notice when you do this is that, so you know your angle is 45 degrees, so you'll do something with sine, cosine, tangent to find PX and PY. And what you should notice is that PY does not change, and PX changes from positive to negative. And so when you do this, you're going to solve it in the X direction and the Y direction. But the Y change in momentum is going to be 0 because I have this side is the same on both sides, right? And then the X change in momentum is just going to be whatever P prime X is minus PX. And then that's how you're going to solve it. Does that make sense? Do I need to do more, Chris? That's good. All right, cool. So, hi, what you got? 30? Ooh, this is a good one. 30 is one of those others, and we have a couple of these on this where they take the process we learned, but then you do some sort of some algebra, and it kind of takes us away from the process we've learned, so that it's a little bit maybe beyond the core of what we're doing in the unit, but it's still worthwhile going over. So the idea on 30 is we've got one ball that has a mass m, and it's making a head-on collision with a second ball, and we'll just call this mass ball, or this ball mass B. And then they're going to collide elastically. And when they combine elastically, m rebounds at a speed that's 0.45 times its initial speed. So if I call this, I'll just call this VA, right? Then I rebound at 0.45 VA. Except I'm going backwards, so it's negative 0.45 VA. And I don't know how fast MB goes, but presumably MB is going that way. And the question is, I need an expression for what MB is. All right. So I'm going to do my knowns and unknowns. It's going to be a little bit different, but I'm going to do my knowns and unknowns. So what I'm basically saying is I'm saying that I'm starting at a VA that's equal to VA. And I'm ending with a VA prime, which is equal to what? Negative 0.45 VA, right? And then we have a mass of A that's, we're calling M, right? We do the same thing with the VB. We're saying VB starts with a speed of 0, and we don't know what VB prime is, but we don't know what the mass of B is. However, from this point, this is an elastic collision, right? So elastic collisions have to satisfy two equations. They have to satisfy this one, conservation of momentum, and then what's the other one? I remember there are two equations always for elastic collisions. There's this one, and then there's, this is on your syllabus, right? So this one expands to MA VA plus MB VB equals MA VA prime plus MB VB prime. So we kind of, we need to be satisfying both of these equations. Good so far, so far. All right. Now we can plug in what we know, right? So we're just saying that MA, we're going to call it M. VA, we're going to call it VA. MB, we don't know. VB is 0. MA is in. MA prime is negative 0.45 VA. MB and VB prime, we don't know. So what do I have? I have MVA equals negative 0.45 MVA plus MB VB prime. Is there anything I can do to simplify this? Go ahead, Drake. This is like 1 MVA, right? So if I add this to the other side, I should have 1.45 MVA equals MB VB prime. Okay, so that's what kind of what this equation simplifies to. We also have to do something with this equation, right? If I look at this equation, VA again is VA. VA prime is negative 0.45 VA. VB is 0, and VB prime is VB prime. So in other words, VB prime in this case should be equal to 1 VA minus 0.45 VA, which is 0.55 VA. Now, what are we trying to get out of this problem again? Trying to figure out what this mass B is, right? What can I do with these two to get that mass B? I should be able to substitute this in here, right? So I should be able to say 1.45 MVA equals MB times 0.55 VA. And the nice thing is from here, my VAs can cancel. And I should get that MB is equal to whatever 1.45 divided by 0.55 M is. So you can calculate that out. That'll be your answer. Sorry, I'm getting off the screen there. So again, as far as the core of the physics of this, what I'm really important in you, what I'm really interested in you being able to do, right? I'm really interested in you being able to solve an elastic collision problem. This algebra that we did, this is kind of outside the core of what I'm going to ask you to do, but every once in a while I like to give you one of those problems just to keep our algebra skills sharp. Is that all right? So, what else? Generally speaking, whenever you have an elastic collision problem, just to, like a review from last time, how do you approach any elastic collision problem? Tell your partner actually, this is a reminder, because that was an elastic collision problem, but it was kind of obscured by the amount of algebra that we had to do. So this, I just want to make sure that we're on the same page with this. So tell your partner real quick, any elastic collision that you have, how do you start that problem with an elastic collision? Okay. Tell your partner what you think. You might want to try. How do you start any elastic equation problem? Go ahead, Bob. You conserve momentum, so sigma p equals sigma prime p prime. You set that equation up, and go ahead, Ray. Well, yes, you could do it. That's the long way of doing it, right? The short way of doing it is this equation, right? So all elastic collisions conserve momentum and obey the elastic collision condition, which is this. Why don't we go ahead and just to make sure we're on the same page, if you haven't yet, why don't we take a minute and do and work through 25, which is I believe on the syllabus. So maybe you've already done it at this point, but if you haven't, I want to make sure that everyone's really confident with this. So take a look at 25. This will be, so we're basically just going to do the homework problem, but I want you to see what you can do with 25. Is 25, it's in essence the same thing as what we just did, except what we just did is way harder, and sometimes I just want to make sure that we can do the important part. So try 25. Sorry, for the benefit of the people watching the recording, right? So we set up our knowns and unknowns, and then we said the two equations we've got to solve are conservation momentum and the elastic collision condition. Oops, sorry, this is MB. So we have this, and then we have VA. So 3.80 plus VA prime equals 0 plus VB prime. So we've set up these two equations now. Andrew, what would you do next? Say again, sorry. Yeah, we can just kind of simplify here, right? So what, that thing's 0. 0.44 times 3.8 is what? 1.672. That's what this equation is, and then this equation becomes just 3.80 plus VA prime equals VB prime. Great review now.
You would plug it in.
Yeah, so you're essentially, you want to substitute this thing into there, right? So we've got 1.672 equals 0.440 VA prime plus 0.220 quantity, 3.80 plus VA prime. So 0.22 times 3.8 is 0.836 plus 0.220 VA prime. Then this is just algebra, right? So I combine those two together and I get 0.660 VA prime. I subtract this one over. I get 0.836. Divide. That's right. Yep. And then we have to finish it up how? Because that's not, we don't just have one answer, we gotta have both. Becky, how do I finish off? Plug that in back here, yep. So if I add 3.8 to it, I've got what, 5.07. And then does anybody remember the check that you can do to see if they're makes sense? Yeah, Emma. Right. Yeah. So in an elastic collision, the difference of velocity should be the same. So the difference between 3.80 and 0 should be the difference between 1.27 and 5.07. And in this case, it's pretty easy to see because of the way the equation worked out. But that's a check you can always do at the end. So elastic collision, and it has to tell you elastic, right? But if it says an elastic collision, you're always setting up those two. All right, you okay with that? All right. The new topic that I want to cover today is momentum in 2 dimensions. So this should take maybe another 20 minutes, and then you'll have the rest of the time to do work. There's really, to call this new information is not quite right, because in theory, you should already know how to do this. It's just combining what we've already talked about with triangles. So when you get this, I want you to start by drawing a diagram of it. So see if you can start with a picture for this. So in essence, you got something like this, right? You've got, yeah, Malachi. You're right. I'm doing this wrong, aren't I? Let me try that again. So let me get a better drawing on a graph look a little bit better. Yeah, you're right. So what we have is ball A hits ball B initially at west, but you're right. So A ends up going this way. All right. At 2.3 meters per second. And the angle is 40 degrees. And then we want to know, what is B doing? So something like that. Is that better? So the idea is, and it's kind of hard to capture all this in a static picture, right? But you're playing pool, right? You're playing pool and you hit the ball, and one ball goes off at an angle, and the cue ball goes out at a different angle, right? And we know the final conditions of one of the balls, and we want to know the initial conditions of the other ball. This is not an elastic collision. I did not say it was elastic, so we can't use the elastic condition. It turns out you can't use the elastic condition for two-dimensional problems anyway. But particularly this is not an elastic collision. So let's think about, so what's happening here, right, is we are conserving momentum. That's all that's happening here, right, is we are conserving momentum. But the difference is that we are conserving, since we're in two-dimension, we're conserving momentum vectors. And generally speaking, how do we deal with vectors? Yeah, we use our components, right? So this, we can split into two. We can say sigma px equals sigma px prime, and we can say that sigma py equals sigma py prime. All right. Well, let's, before we go any further, it's probably going to be important to find components, right? So here's what I'd like you to do to start with. I'd like you, and you're going to need some more room to do this, but I'd like you to see if you can find all of these things. Or as many of them as you know. PAX prime, PAY prime, PBX prime, PBY prime. All right, so we have two objects. They both have an initial and final, and they both have X and Y's, right? So I have PAX, PAY, PBX, PBY, and all of those primed as well. I want you to see if you can figure out as many of those as possible. There's some of them that we aren't going to know yet, but see if you can figure out as many as possible. So I'm going to give you a few moments with your partner to see if you can get as many as possible here. There are 4 of these that are easy. Does anyone know the easy ones? Anyone know any of the easy ones? Go ahead, Chris. Yep. Yep, I'm not. And B is at rest. Oh, we have that. Okay. Oh, I should be careful. That's not PAX though. That's BAX. What's PAX? Leo, you know what it is? Should be 18, right? Because we got to do MV, right? So the V is 3, momentum is MV, so if the mass is 6, the velocity is 3, so this is going to be 18 kilogram meter per second is going to be the PAX. All right. Now, of these, there are 2 that are possible to find and 2 that aren't yet. What are the 2 that aren't possible to find yet? Probably these, right? We don't know how fast this one's going yet. But we do know how fast this is going, right? And we do know the angle that it's going at, right? So in other words, what we know is that PA is, well, let's see here. So the VA is 2.3. So let's get that into a P first. What is that? 13.8, is that right? Somebody check me on that. I think that's right. Okay. So we know that this is 40 degrees, 40 degrees. And so we're going to have to do some sine and cosine stuff to figure out what PAX and PAY are. Primes, these are all primes. I might have either of these. Go ahead, Leo. Did you multiply that by 13.8 yet? Are you in degree mode? All right, that makes sense then. Say again. That sounds reasonable to me. Did anyone else get that? Yeah, okay. Anyone get this one? 10.5 says that what you got, Ainsley. Okay. So now we know I can put these up here so I know 10.57, 8.87, right? Now, what we in essence have, right, is we have to do conservation of momentum twice. So we need PAX plus PBX to equal PAX prime plus PBX prime. And we need PAY plus PBY to be PAY prime plus PBY prime. Okay, so we need 18 plus 0 to be 10.57 plus PBX prime. And we need 0 plus 0 to be 8.87 plus PBY prime. So I think what you're going to get is you're going to get a PBX prime that's something like 17.43. No, 7.43, right? If I subtract this over, I get 7.43. And then if I subtract this over, I should get negative 8.87. So now we can find what PB prime is, and we can find what its angle is. The Pythagorean theorem in inverse tan. What's up? Okay, what I did to get this was I did a squared plus b squared equals c squared. And what I did to do this was inverse tangent, right? Opposite over adjacent. So to be clear, that is your P prime B vector. If instead I wanted to know the V, that's not how you write that. P equals MV, right? What I could do is I could divide that by the mass, And so the actual velocity is going to be 1.93 meters per second at 50 degrees south of east. The only thing that makes this one tricky, so the algebra is no different in either the x direction or the y direction. The thing that makes this tricky is that you've got to do the trigonometry to get the x direction or y direction. All right. Okay. If you look on the, I only have one problem like that on the syllabus, and then I think I believe I have a bonus. So that's about what you could expect on the test. You could expect that this would be a bonus for the question. So oh, I don't have a bonus. I'm gonna have to change that. I'm gonna have to look and figure out what I want the bonus to be. That's all right. You have 35 minutes to work on your syllabus.